Okay, so we're going to continue on here, chapter 12. We were talking about bonding last time, and we really kind of focused in on drawing Lewis structures for covalent bonding or molecular compounds where they share electrons. Remember that when you draw Lewis structures, a few things are kind of important, and it's sort of the arrangement of everybody. Remember that hydrogen and fluorine should not be in the middle. Should usually be the least electronegative atom. Should usually occupy the middle. Usually, if you have one element and a few atoms of another, the one element's in the middle. Everybody else is attached to them, but again, not in all cases. Um, then we want to make a single bond, right, from the central atom to each of the outside atoms. We also have our total number of valence electrons. And that's going to give us, in this example, for example, here, 4. Rest of them will go on as pairs on the outside until the outside ones are filled. And if you still have more, then to the center you go. And at that point, hopefully you have done all of your electrons. If somebody is not meeting the octet rule, then remember you want to try to fix it with a double bond. And when we make double bonds, we do bring a pair of electrons in to make that bond. So we just don't add extra. If you sort of exhaust all your double bonds, then you want to kind of make a triple bond. At that point, it should fix your problem. And again, we would bring electrons in to make that triple bond. Any questions on any of that there? If I'm not mistaken, do we have 2 more to draw? Is that what we had left or something like that? So I can go off my memory here. It was HNO3, right? And was it CO3 2 minus? Is that the other one? Okay. So these are the 2 that we had. All right. So let's take a look at these here and to draw it. So this one, we'll start with the CO3 2 minus, why not? And in this case, we will take the number of valence electrons, which is equal to the group number. So that's going to be 4 for our carbon. There's 3 oxygens. Each is group 6, which means it has 6 valence electrons. And once again, we do have to take into account here, this thing does have a charge of -2, and minus means it has gained electrons. So we do have to add that to our total. So here we would have +2 more. So that's like 18, 20, 24 valence electrons. In this case, we really have 1 carbon and 3 oxygens. Carbon should go in the middle. In addition, if you look on the periodic table, carbon and oxygen are on the same row there on the periodic table. Carbon's further to the right, which means it's more electronegative. So definitely carbon here should be in the middle. So we're going to do carbon in the middle, oxygens here. We're going to again do a single bond to each of them. That's going to use 6 electrons. That leaves us 18 more to go. We're going to put on the outside. So 2, 4, 6, 8, 10, 12, 14, 16, and 18. So at this point, we have now placed, again, all 24 of our electrons. We always want to make sure that everybody meets the octet rule, obviously, except for hydrogen, that should only need 2. Is everybody good in this case? Nobody's good. Not everybody's good, but carbon is not so great here. It only has 6, right? Everybody else has 8 electrons. So here we do need to make a double bond. In this particular case, every single oxygen here is pretty much the same. So you could choose any oxygen to do the double bond with. Remember again that we're going to actually take a pair of electrons, by circling both there, and bring them in to make that double bond. So when we do that, we'll end up with something that looks like this. If I draw it, maybe. There we go. Like that electron went way too left there. Let's try to fix that maybe. And now what we have is a picture that has 24 total electrons, and everybody does have 8. Remember that if it is something with a charge, typically we do kind of put brackets around it and the charge on the outside. Again, we could have drawn 2 other structures if you double bonded in the other locations. So if I double bonded over there to the right, we would end up with something like this. And if I double bonded there to the left, we would end up with something like this. And remember that any one of these three structures are okay to draw. They are related to each other as what we talked about, which are known as resonance structures. And resonance structures, again, basically develop because those double bond electrons we bring in to make that double bond are sort of delocalized, which means they're just kind of moving around. So at any given point in time, they could be over here, they may be up here, maybe over there. So the true structure is probably somewhere between all three of those. But we could draw multiple Lewis structures because we have the option really to kind of move the double bond to some different locations and stuff like that. So once again, as we talked about last time, if you're asked just to draw a Lewis structure, any one of the three would be okay. If you're asked to draw all the resonance structures, then you should draw all three of them. Any questions on that one there? Coming out to our other one here, which was nitric acid. And I think I gave you sort of the arrangement that it is something like this. So we'll count up our valence electrons here. So hydrogen has 1, nitrogen has 5, and 3, oxygen's at 6, 18, 19, also at 24 in this case. So although there are multiple sort of atoms, and in this case there would be multiple central atoms, the nitrogen and the oxygen there, in the middle would be considered central atoms. We still approach it the same way. We just make a single bond to everybody in this case. And in this case, we now have 2, 4, 6, 8. We have 16 more to go. We still do the same thing we did before, which is kind of work outside in. So we're going to put our electrons on the outside ones and then kind of work ourselves towards the center. Am I going to put any dots on the hydrogen? No, right? Because it's done. So remember, no dots, no double bonds, triple bonds with hydrogen. But we can put some here. So that's going to be 2, 4, 6, 8, 10, and 12. At this point, I have a total of 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I still have 4 more electrons to go. The next sort of outside atom would be the oxygen. Here's where you would want to go next. Again, kind of working your way out and in. We could put a couple of pairs right there to get our 24 electrons that we need in this particular case. Is everybody good on this one? There's not nitrogen here. Again, is going to be a little bit short. So we do have an option to make a double bond. Really, you could kind of make it at all three of them, but the two likely candidates for a double bond would actually be these two here. I say that because, frankly, this is what makes it an acid, this OH bond here. That hydrogen comes off, and that's basically what makes it an acid when it goes for a swim. So most likely, you probably double bond to the left are the right there when we would do this. So we'll take this and bring it in, and we would get something that looks like this. And this is another one we could draw a resonance structure for if we double bonded there to the left as well in this particular case. Questions on that there? So as we talked about last time, I would highly recommend you follow the steps we've been talking about to draw these. This should lead you to a pretty good structure in the end. Again, don't try to do piecework, and again, no double bonding, triple bonding, sort of right out of the box. Any questions on drawing any of those there? Yeah. Then let us continue on as I scribbled clearly across this page here. So let me just get rid of that there. There you go. All right, so we talked a little about resonance, but let's talk about bond length, and you don't need to memorize the numbers or anything on this chart. But this is a chart of bond length and the different types of bonds, single, double, and triple. And if we look at the single bond for a carbon-carbon, a double bond, and a triple bond, for example, we see that the single bond is 154, double bond's 133, and 120. We also look at like carbon nitrogen, single bond 143, double bond carbon nitrogen 138, and 116 as we triple bond. What we see in general is this: as we continue to add bonds, the atoms get closer together. And that makes sense because you're bringing electrons in between them, which are negatively charged. So a bigger negative charge in between the atoms, attracted to the nucleus of the atoms, which are positive, just going to kind of bring everybody in. If you make a triple bond, going to come on in a little bit closer as well. Again, bringing a lot more of that negative sort of charge between the two atoms, going to attract the nucleus of both atoms in. So every time you sort of add a bond, the distance between the different elements or atoms gets smaller and smaller. But like somebody was backing up there, I'm not sure. And that's the general trend that we see. That's also really important in terms of strength. In terms of bond strength, a triple bond is stronger than a double bond, and a double bond is stronger than a single bond. Double bond's not like twice as strong or anything like that, but that's just a general pattern. So I think of it like a pencil, right? If you had a brand new pencil out of the box, right? It's nice and long. You could just snap that thing pretty easily with not a lot of energy. If you take a couple of chemistry exams, you got like a nubbin and an eraser left like that big, right? And you try to like snap it. It's good luck with that, right? Everything's just really close together. You're not going to be able to snap it really easily. So again, because everybody just gets really close to each other as you continue to have those bonds, it takes a lot more energy to break those bonds as you go from a single to a double to a triple. Any questions on that there? Now, resonance structures, as we just talked about, as we were going through our drawings there, are really structures that you could draw multiple Lewis structures to represent a single molecule, because one Lewis structure doesn't really sort of explain what's going on in terms of their electrons and their bonds. And that's really for a lack of a really scientific explanation. Pretty much you could just, anywhere you can move the double bond, if you have multiple options, you could draw another structure, and they're sort of equivalent to each other in terms of that. Typically, those structures are separated by this sort of arrow headed in both directions. And again, like we saw in carbonate, we just kind of moved our double bond from one spot to the next. So here's an example, for example, of ozone. We could double bond over here on the left. We could also draw an equivalent structure where we double bonded on the right. The pluses and minus, don't worry about this. Not too important. That's what's known as the formal charge. But we could have two equivalent structures when we go to draw something like ozone. And then obviously our carbonate that we did. Those are, again, the three structures we just drew. And in case you're curious, that is where the -2 charge is. -1, and each of the single bonded oxygens carry actually a -1 charge, and that's why it's -2 overall. Benzene is something that if you take organic, I'm sorry, but if you take organic, it will look something like this. This is a benzene ring, badly drawn. I'll get thrown out organic probably for drawing it like that. But basically, each of these spots are carbons here, and it has 3 double bonds. And you could draw a resonance structure where the double bonds are on the other side. And sometimes you even see benzene drawn with a kind of circle in the middle to indicate that those double bond electrons are just kind of moving around the ring and stuff like that. So we won't see too much of benzene, I think. But again, when you get to organic, you'll draw a lot of that ring there. And just another example. So we'll just kind of go through that one there. All right. All right. So although everything in this particular class here that you are asked to draw and so forth, yeah, you do not. On the actual atoms, you do not, like it was there in the carbonate. Is that what you're asking? You don't. But you do need to put a bracket around it like we did and put the -2 on the outside. So that negative that's on that drawing, which I think this is what you're asking. Any of these guys, I guess. Like these, do you have to put the negatives here? Is that what you're asking? Yeah. Yeah, you don't have to do that, but you do, like we did before, has to put the whole thing in brackets and put the -2 on the outside. This is something we're not going to talk about in this class, but this is what's known as formal charge. And formal charge is basically what each of those elements have in terms of their charge based on how they're sharing their electrons. So, and that's where, again, when it's CO3 2 minus, that's really where, for example, the -2 comes from. It's from the sort of charge that's associated with those two oxygens in this particular case. All right, so everything will obey the octet rule in here that you're asked to draw, but there are some exceptions to the octet rule, and you do need to be aware of the exceptions to the octet rule, although you will not be asked really to draw any of them in this particular class. The first exception to the octet rule is what's known as an incomplete octet. And much like the name implies, it means that it actually is perfectly fine with less than 8 electrons around it. So your three sort of ones that typically would go incomplete is beryllium and aluminum and boron. Out of those three, really boron is probably the one that you would see the most in an incomplete octet, as beryllium and aluminum are kind of like metals, so they're probably not going to do too much of covalent bonding, even though, maybe that BeH2 doesn't really exist. It's just an example people use. But boron was sometimes referred to as being an electron deficient, and is perfectly fine with, less than 8. In this case here, boron has only 2, 4, and 6. And again, it's okay with that. So I would say probably that boron is going to be the most one that you would see in an incomplete sort of octet. A couple of other exceptions, which are sort of important as well. The next one is what's sometimes referred to as an odd electron molecule, which means when you add up the total number of valence electrons, you get an odd number. And if we put everything on in pairs, if you have an odd number, that means somebody's going to be lonely, right? And be just one by itself, unpaired electron. They're kind of like chlorine, for example. Free radicals and up in the atmosphere have a lot of single electrons, and they're very, very reactive because of that. That's not really a great situation that they want to be in, so they try to react a lot to sort of fix that situation. But here in NO and NO2, if you draw the Lewis structure, you would end up with one unpaired electron in each of them. Now, probably the most common exception to the octet rule that you will come across when you go into 1A is the expanded octet. Pretty much you draw like all those things in 1A. So the expanded octet is pretty much what it sounds like as well. The expanded octet is guys that can actually go over 8 electrons, and they could go upwards of 10 or 12 electrons. And the ones that can do that is, if you look on the periodic table and you find your friend sulfur, and you go to the right of sulfur, go to the left of sulfur, and go down on sulfur, all in the non-metal region, sort of, as you do that on the periodic table. Those are the elements that have the ability to do the expanded octet and really handle those extra electrons. And the reason is, if we went in order and did chapter 11 before we did this chapter 12, it's because of sulfur is on group period 3 of the periodic table. And period 3 of the periodic table relates to the third energy level in terms of where electrons are in terms of the atom. And it's on the third energy level that we first start to see the appearance of what are referred to as d orbitals. And d orbitals, s orbitals, and p orbitals are where electrons are found in the atom. And that is where we first start to see those d orbitals being available. Now, although these elements may not be using them, they have those orbitals available to stash all the extra electrons. So they have a place to put them. And that is why when we hit sulfur right, left, and down, anybody past there has those d orbitals available to stash all the extra electrons that they need. That is also why, though, if you go above sulfur on the periodic table, little NOF and period 2, period 2 only has s's and p orbitals. They do not have d orbitals, and that's why those guys should never, ever go over 8. So they can never go over 8 because they have nowhere to put them. So the short story is, At sulfur and below, they essentially have extra orbitals or locations to house all the extra electrons, so they're able to do that. So here, for example, SF6, if I don't draw all the dots on the fluorines, as you can just look at the sulfur contribution here, it's got 2, 4, 6, 8, 10, and 12 electrons around it, and it's perfectly fine. This is also why if you Google answers, you will see things where they have more than 8 around it. For example, if we were to draw sulfate, which is SO4 2 minus, if you follow our rules and obey the octet rule, you will end up with this picture, which in this class is probably the picture you should end up with, I would imagine, since we're obeying the octet rule. Now, if you Google sulfate, you will see this picture, with some double bonds and some single bonds happening. And this guy obviously now has 2, 4, 6, 8, 10, 12 electrons around it. And they're both technically correct. But for our class, this is really where you should end up by obeying the octet rule, because if you go through our steps, you'll end up with that picture at the end, and everybody's good. Everybody's got 8, everybody's fine. The truthful story is when you get to 1A, you'll learn that actually this is a much better picture, a much better Lewis structure with that, because of what I just talked about a second ago, formal charge that we don't talk about in this class. So based on formal charge, you would draw the guy on the right. Based on how we do it in here, you draw the guy on the left. So draw the guy on the left. Don't Google answers, because your teacher will know you did that because we didn't talk about, drawing those things. Yeah. Any questions on that there? All right. So once again, octet rule will be obeyed in this class, but you are responsible to know the 3 different exceptions and sort of what they are. So basically less than 8, odd number of electrons, and more than 8. Yeah. Any questions on that there? All right, so then let's talk about molecular geometry. And molecular geometry refers to the 3-dimensional arrangement of the atoms and their electrons in space. Molecular geometry cannot be predicted from Lewis structures, but you can use a properly drawn Lewis structure and how many bonds there are and how many electron pairs there are around, say, the central atom to figure out what the geometry is. So when we do geometry, it is always about, when you have 3 or more atoms, it is always about the central atom. That is the most important one. What's happening with the guy in the middle? And that's always what you want to look at. So when we do geometry, that is definitely what you want to look at. Now, the basis of this approach is known on the idea that valence electrons basically don't want to be around each other. And that makes sense, right? Because electrons are negatively charged. So when you get a bunch of electrons near each other as they're making bonds, they frankly, as odd as it may sound, do not want to be near each other. And what they actually try to do is get as far away as possible, but they can't escape. So they try to move themselves as far away as possible. But as they are moving themselves away from each other, what happens is the overall shape of the molecule and the things that are bonded are moving as well. So the overall shape of the molecule will change as they try to sort of escape each other, and they can't really escape each other. So this approach is what is known as the valence shell electron pair repulsion model, hence the abbreviation VESPER. And it does account for 2 types of molecules. One's where you look at the central atom and it has no lone pairs. So basically, when you draw your Lewis structure, there's no dots around the central atom. So, they're all bonds, there's no dots happening. And central atoms where we do have lone pairs. So when you draw your central atom, you got some dots there, maybe 2 dots, 4 dots, however many dots may be present. So there's a couple things that we want to keep in mind as we go through this. And really the first one is most important there. And it is if you draw a Lewis structure and you have a double bond or you have a triple bond. So it doesn't matter, double bond, triple bond. It counts as one electron pair and one bond. And that's really important because, frankly, most of us, myself included, cannot visualize what things look like in three-dimensional space in their head. So probably the best way to learn geometry is to just remember two electron pairs, two bonds. That is linear type of geometry, or three electron pairs, three bonds is this geometry. And that's really probably the best way to do it. So we're going to kind of make a table as we go through it. And you can kind of make a table, and we'll see one at the end, and there's one in your book. But that's really the best way to sort of remember the names, is to just memorize how many electron pairs, how many bonds there are, and the names that go with it. Again, a lot of people can't sort of visualize it. The other thing there is, as we talked about, we could draw resonance structures. So if you draw a proper resonance structure, you could apply the geometry to any of the structures. And in most cases, all of the structures that you draw that are resonance structures will end up with the same geometry in the end, usually, and stuff like that. Now, one more thing before we get going on this, we are actually going to talk about two different types of geometry names. Okay, so the first type of geometry name is what is known as the electron pair geometry. And I'm just going to abbreviate that as we go through here, EP for electron pair geometry. And electron pair geometry is a name that's given based solely on the central atom and how many electron pairs there are around it. So it doesn't matter really how many bonds or anything like that. It's just how many total electron pairs there are. It is, in theory, where those electrons are in three-dimensional space, sort of the geometry of just the electrons that are present. The other type of geometry that we're going to talk about is what is referred to as the molecular geometry name. And I'm just going to call that MG as we kind of go through the lecture here. And sometimes people also refer to this as the shape of the molecule. So the molecular geometry takes into account how many electron pairs there are around the central atom and how many bonds there are. And based on the type of electrons there are around the central atom and the number of bonds, what will happen is things will start to try to move away from each other, and the actual overall shape of the molecule will change. Now, as we will see, some cases, both of these names will be the same. And in some cases, the names will be different between the two. And really, the only name that changes is the molecular geometry name, and we'll talk why that changes as we go through it. But in certain cases, we will have the same name for both in a situation. In some cases, we'll have two different names, one for electron pair geometry and one for the molecular geometry. Any questions on that so far? All right. So let us get into it, and let's really just start with, and there's lots of letters and symbols, and you don't want to worry about it, don't worry about it. But let's talk about really the simplest geometry that you could do. And it's really because there is no central atom, and that is a diatomic molecule. And diatomic molecule, as we've talked about, is basically just two. So you got yourself like an F2, right? Got maybe like an HF, got an O2, got yourself an N2. So all four of those that I just drew, they're all various things. We got two of the same elements. We got two different elements. We got single bonds, double bonds, triple bonds. In terms of geometry, it doesn't matter. The old saying is the shortest distance between 2 points is a straight line. Yeah. And that's the idea here. The only way you could arrange two things that are connected to each other is in a straight line, right? So the geometry for anything that is a diatomic molecule is pretty much linear, and that's always going to be linear. And it's just because you have two things. There's no other way to arrange those things other than a straight line, and it will always be linear. So like I showed you here in these pictures, doesn't matter if there's double bonds, triple bonds, doesn't matter if they're different elements. You see two things, you're asked what the geometry is, just write linear and you'll be right. Yeah. Any questions on that there? All right, so that'd be nice if everything was that easy, but of course it's not. So let's talk now about really what we're going to talk about is three or more atoms involved. So here we're going to have a central atom, a guy in the middle. So an example of this, for example, is beryllium chloride. Now, when we look at the Lewis structure that is drawn, there's really two things that you want to look at. And we always want to focus in on here the central atom. So when you're doing geometry, it is always the guy in the middle. That should be the only one you're concerned with when you're doing geometry, is that element in the middle. So the two things that we want to think about is the total number of electron pairs and the total number of bonds. So when we look at the beryllium here, it has a total of 2 electron pairs. One there and one there. Yeah, 2 electron pairs. And in terms of bonds, how much does it have? It also has 2, right? One there and one there, right? Those are also bonds. So first off, something with 2 electron pairs around it, the electron pair geometry. Again, I'm going to abbreviate as EP. It is known as being linear. Now, with those 2 electron pairs, it also has those 2 bonds, which means the molecular geometry in this case will also be linear, or the shape. So why is that? It is because of this. There are only 2 bonds, and those electrons do not want to be near each other, so they end up going as far apart as they can, which is opposite of each other in this case. And because they are bonds, those atoms that are attached go for the ride, right? So as those electron pairs move, so does those atoms move, and the whole shape of the molecule now is going to line up in a straight line, and it's going to end up being 180 degrees apart, which is the bond angle, which you do need to know as well. So the bond angle, by the way, is 180 degrees, and the bond angle is based on the electron pair geometry. So because these are bonded atoms, those atoms go for the ride, and that is as far apart as they possibly could get from each other. Is basically on opposite sides of the straight line. Any questions on that? So if you want to make a table as we go through, these are the 2 things that you should sort of list, and these are the 2 names that go with it. Let's take a look at another example here. This is boron trifluoride. This is also an exception to the octet rule. It's less than 8 and it's okay. So we're going to look at number of electron pairs. Once again, it is the central atom that we are interested in. And we got 1 electron pair, 2 electron pairs, 3 electron pairs. And the number of bonds in this case is also going to be, in this case, bless you, 1, 2, and 3 bonds, right? So whenever we have 3 electron pairs involved, the electron pair geometry name is what is known as trigonal planar. Some people call this triangular. Now, with those 3 electrons pairs and also the 3 bonds, what happens is these electrons here in those bonded pairs are going to try to get away as far as possible. Now, you remember with 2 bonds, they're able to get like 180 degrees away from each other. But what happens in this case is these guys are trying to get away from each other. These guys are trying to get away from each other. But now we can't bring these guys too close to each other because they don't want to really get away from each other. So because of that extra sort of bond that's present, they can only manage to get this trigonal planar geometry as well. So the name of the molecular geometry is also trigonal planar. also known as triangular. And the reason they call that is they're able to get apart about 120 degrees and make, as we like to say, an equilateral triangle. Yeah, that's basically what it makes. The bond angle here is 120 degrees. And again, makes sort of a triangle type shape when you look at it. And again, with the presence of that extra bond, it doesn't allow everybody to get as far apart as possible. They kind of got to move back and forth, and they end up in this more triangle type shape from each other, where they sort of end up in the corners, basically, of the triangle. And again, that's as far apart as it can kind of manage in this situation. Any questions on that there? All right, the next example is, as you can see there, triangle. Something with a central atom and 4 things attached. So again, we're going to look at the central atom, and we're going to count up the number of electron pairs. And that is 1, 2, 3, and 4. And the number of bonds in this case also going to be 1, 2, 3, and 4 in this case. So we do have 4 bonds happening. Now, something with 4 electron pairs will give an electron pair geometry known as tetrahedral. And once again here, we're now adding a 4th atom to the mix, which means just like before, everybody's going to try to get away from each other, but now we got an extra pair of electrons in the way. So they're going to have to kind of move around. And the molecular geometry will actually end up being the same. It will actually be what is known as tetrahedral. And that will end up being a bond angle of 109.5. It kind of makes like a triangle on the face of it and almost pyramidal on the bottom. Again, these guys are trying to get away from each other. These guys are getting away. Those, and then again, these 2 guys are also trying to find some space between them. And again, with that extra bond there, things can only spread out so far from each other. Any questions up to there? And again, bond angle 109.5. So up until this point, when we look at the electron pair name and the molecular geometry name, are they the same or different? They're the same. And that's always going to be the case when you have no dots on the central atom. So when you have no dots on the central atom, the electron pair geometry and the molecular geometry names are going to be the same. And the reason for that is because you only have one type of electrons, which are bonding electrons, things that are involved in bonds. So because there's only bonding electrons there, as those bonding electrons move, so does the atoms move. And the overall shape ends up the same as the electrons in that particular case. Now, when we start to introduce non-bonding electrons on the central atom, the dots basically. So when we start to introduce those dots on the central atom, this is where we actually start to see some differences in the names. And the actual name that's going to change is just the molecular geometry name will change. So as we introduce those non-bonding electrons, that molecular geometry name will change. The reason for that is a couple things. The electron pair geometry name will stay the same because there's still the same number of electrons around the central atom. They'll still sort of space each other out as possible. But in order to have non-bonding electrons on the central atom, that means that you no longer have like one of those extra bonds that we had in these situations. So you have like a missing atom. So that allows those electrons actually a little bit more room to move from each other because they don't have this atom moving with them in that third situation, for example. And it changes the overall molecular geometry shape because it has that little bit more room to kind of move away, and we end up getting slightly different overall geometry shapes because of that. So that the appearance of those non-bonding electrons and the disappearance of some of those bonds that are there creates a little bit more of an opening for these guys to get away. There's actually another situation that occurs as well, which is depending on the type of electrons that are present as to how badly they do not want to be near each other. So The best situation is the situation that we just were talking about, where we have bonding electrons near bonding, so lines near lines. That's like the best situation in terms of repulsion. They can kind of get away from each other, is okay. The next kind of worst situation is where you get dots near bonds, basically. So non-bonding electrons near lines near the structure. They don't like to be near each other. They're going to try to move away a little further because they have those extra room because of the dots. The worst situation in terms of when electrons get near each other is when you got non-bonding electrons near non-bonding electrons. They do not want to be near each other. And because there's no extra atoms present, they find a way to sort of get as far away from each other as possible. And that really affects the overall shape of the molecule as they sort of go one way or the other, as the bonded atoms will start to move. So that's like the worst situation. And also where you'll see a kind of the biggest sort of change in the molecular geometry sort of shape of it. All right, so let's take a look at some of these. The first one's going to be sulfur dioxide. And if you draw up a little sulfur dioxide, which I think we might have earlier, will look something like this. And once again, we are going to look at the central atom as the most important thing here. And we're going to count the number of electron pairs. How many electron pairs does that sulfur have? Doesn't matter if they're lines or dots. Has one here, yeah. Has one here, and it has how many here? It actually only has one. So remember that when you're doing geometry, double bonds or triple bonds count as only one electron pair. So effectively, it has only 3 electron pairs. Now, in terms of bonds, the number of bonds would be in this case 1 here and only 1 here. So it also counts as only 1 bond, and it essentially will have only 2 bonds in this case. So double bonds or triple bonds count as 1 electron pair and 1 bond. Now, as I mentioned before, the electron pair geometry name is always based on how many electron pairs. So we saw it earlier, something with 3 electron pairs is still trigonal planar. Now, in this particular case, we have bonding electrons near bonding electrons. We have non-bonding electrons near bonding electrons. And what's going to happen in this situation is our bonds here are going to try to get away from each other. And definitely this guy is going to make these guys get away from each other because they don't want to be there. So what ends up happening is the oxygens find themselves kind of angling down in this situation. And it becomes a molecular geometry known as, I'm going to call it angular. I will say that some people will call it bent. Some people will call it bent angular as well, but we're going to go with angular in this case for 3 electron pairs and 2 bonds. And the bond angle in this case is going to be less than 120 degrees. So it is still based off of 3 electron pairs, which is 120 degrees. But because of those non-bonding electrons, it kind of folds to a little bit less than 120 degrees with those non-bonding electrons kind of coming upwards and our guys kind of spreading down and again trying to keep some distance between each other as they move around. So 3 electron pairs, 2 bonds, electron pair geometry still trigonal planar because there's 3 electron pairs, and our molecular geometry will be angular in this case. Looking at another example here, a little NH3 action. We draw NH3, and again, we're going to look at the central atom. The number of electron pairs is going to be 1, 2, 3, and again 4. So when you're counting electron pairs, doesn't matter if they're dots or lines. And again, double bonds and triple bonds count as only 1. So that's 4 electron pairs. Number of bonds in this case is only going to be 1, 2, and 3. Once again, based on the electron pairs that are present, the electron pair geometry is going to be 4, which is still tetrahedral. We again have non-bonding electrons near bonding electrons, which is not great. Bonding electrons near bonding electrons, which is okay. So what's going to happen again, because of these non-bonding electrons that are present, these bonding electrons are going to try to get away from each other. But once again, they also can't get too close to this bonding electrons, right? So they're going to kind of spread out in that situation. And as you can kind of see there, it will make what is referred to as trigonal pyramid, make sort of a pyramidal shape there on the bottom. And that is what the molecular geometry name is, trigonal pyramid. It has a bond angle of less than 109.5. It's about like 106-ish, I think, somewhere in that ballpark. So somewhere in that ballpark. But it'll have less than 109.5. So again, it makes this trigonal pyramid type shape when it's all said and done as it comes down there. And again, everybody's trying to keep really kind of their distance between everybody. Now let's take a moment to talk about two names that we just talked about. Trigonal pyramid, which is 4 electron pairs and 3 bonds. 3 electron pairs and 3 bonds, right? Is trigonal planar, yeah? They are different. So on an exam, you cannot just write trigonal and let me choose, because I'm going to choose with an X. Yeah, so don't let me choose. Don't let me do the other thing that I like as well. I'm super confident it is trigonal. I'm writing it big, and I know it starts with a P. As clearly planar. Which one was it? I'm not really sure. So make sure you choose. Don't just write trigonal. And there is a difference between those two. Again, trigonal planar is 3 electron pairs and 3 bonds. Trigonal pyramid is 4 electron pairs and 3 bonds. Any questions on that? The good news is the last geometry that you are responsible for. By the way, when you go to 1A, there's a lot more geometry for all those expanded octets that you do. Something like we see here in our friend water. Water, again, we're going to look at the central atom, which is our oxygen. And frankly, it has, in terms of number of electron pairs, that's going to be a 1, 2, 3, and 4 electron pairs. The number of bonds here going to be 1 and 2 bonds only. So once again, the electron pair geometry name is going to be based on the number of electron pairs. So that is still going to be tetrahedral because it has 4 electron pairs. In the case of water, we have all of the horrible electron interactions happening. We have bonding electrons near bonding electrons. We have non-bonding electrons near non-bonding electrons. And we have non-bonding electrons near bonding electrons. So what happens in this case, as I mentioned before, these non-bonding electrons like try to get away as far as possible. And these bonding electrons also try to get away from them. So as those electrons kind of go up, the guys with the bonded atoms go down to get away from them. And once again, they can't get too close to one another here either. So they end up with a molecular geometry shape known as bent or V shape, which is why we are not going to use bent for our angular. And the reason for that is the bond angle here is less than 109.5. It's about 104-ish or so. So it's significantly less than like the 120-ish less. So there is a difference in those things. So 4 electron pairs, 2 bonds. We have bent or V-shaped. Once again, here we see that as we introduce those non-bonding electrons, the molecular geometry name does change. Question on any of those geometries there? So here is a table from your book, or similar to a table in your book. I think that might be more like what it looks like, but they're both about the same. that has these different geometry in our electron pair arrangement and our molecular geometry or structure or shape. I think they both kind of list it that way. You do need to know the name of the electron pair geometry for all the ones that we just talked about. You do need to know the molecular geometry name. And you do have to kind of just know it. So that's probably the best way to do it, is just to make a table of number of electron pairs, number of bonds, and what the geometries that go with it. So if we look at some of the ones that we drew previously, I think we had this. We had this. I'm not going to draw all the electrons in there on the outside. We also had this. We also had this, right? Dare I say we had this that we also drew. All right, so if we wanted to do geometry, right? We want to look at the first one, and actually, let's do what else? We'll just we did this one, I think, too. There we go. All right, so we're going to look at the central atom, right? Number of electron pairs is how many in that case? 4. Number of bonds is 4 as well, right? So 4 electron pairs and 4 bonds. 4 electron pairs and 4 bonds means the electron pair geometry is going to be tetrahedral, right? And the molecular geometry will also be tetrahedral, as they're right there. Yeah, so actually down, where to go? Right there. I went too short. Right there. And again, there's no dots on the central atom, so both names should be the same, right? We come down to this guy. How many electron pairs on this guy? 3 electron pairs. Remember, the double bond counts as only 1, right? And number of bonds would be 3 as well. So we got 1, 2, 3 of both. 3 electron pairs. The electron pair geometry is going to be our trigonal planar, right? Molecular geometry is going to be the same in this case, right? Trigonal planar, as there are no dots on the central atom, so they're both going to be the same. This guy right here, how many electron pairs? 2. Again, each double bond only counts as 1 electron pair, and number of bonds would be 2. So with 2 electron pairs, the electron pair geometry is going to be linear, right? And the molecular geometry in this case will be linear as well, as obviously there are no dots on the central atom, so they're all bonding electrons. This guy's geometry would be, yeah, linear. That's a diatomic molecule, right? There really is no kind of molecular geometry, electron pair geometry, molecular geometry, sort of the molecular geometry. There's not really a bond angle or anything like that, because it's sort of no central atom, right? And stuff like that. So that's what that would be. How about this guy? Electron pairs on this guy. 4. And bonds? 2. So 4 electron pairs means the electron pair geometry should be tetrahedral because of the 4 pairs. But with only 2 bonds, the molecular geometry should be what? Should be, yeah, bent or V-shaped, right? So that is the way that you should approach it. Always the central atom. Just break it down to number of electron pairs, number of bonds, and just know the names of the geometries that go with it. Now, I did draw this guy on the bottom here, which maybe I'll draw somewhere over here. Now, what happens if we do have something like this, which is obviously, as we talked about earlier, something that has multiple central atoms, right? So we'll just put in everything here. So we can do geometry for each central atom separately. So for example, if we were going to focus in on the nitrogen, what we would essentially do is kind of just put our hand over that part of the molecule. But this bond that's going in here still counts for the nitrogen. So we just kind of cover up that side. So with just looking at that side where the nitrogen is, how many electron pairs does the nitrogen have? Yeah, it does have 3 electron pairs, right? And bonds it would have would have 3. So the nitrogen's electron pair geometry would be trigonal planar. And the molecular geometry for nitrogen would also be trigonal planar, right? So they would have the same geometry there as well. Now what we would do is basically switch this around and kind of put our hand over the nitrogen part and just look at the oxygen and just kind of do it this way. And again, the line going into the oxygen still counts for the oxygen. So when we look at the oxygen, how many electron pairs for the oxygen? It does have 4. How many bonds? 2. So the electron pair geometry for the oxygen would be tetrahedral. The molecular geometry for the oxygen would actually be bent or V-shaped. So if you were to have built this molecule with a model kit, what you would see is something like you would see something where through the nitrogen you have that triangle type shape. Then when you look at the oxygen, it would have that bent or what is sometimes referred to as a V shape, yeah, as it will make this, it will kind of curve back up like that, like a V or something like that, or even go down and curve down that way. So you would actually have 2 different sort of geometries that would happen in that case. So if you happen to come across something where there's multiple central atoms, you basically just put your hand over one half of it and just do each atom, central atom at a time, the same way as you would do any other sort of geometry. Any questions on that there? All right. So the last one we're going to talk about here in terms of bonding is polar molecules. And earlier in the chapter, we talked about bond dipoles, right? So we talked about bond dipoles. And remember, bond dipoles is where we kind of use that arrow that points to the more electronegative side, right? The more negative side and the more positive side here. And we used our difference in electronegativity values to figure out our bond dipoles. So bond dipoles or bond polarity talks strictly about just the bond between 2 atoms. You know, is it going to be polar or non-polar? Molecular polarity is talking about the entire molecule as a whole. So the entire molecule as a whole, if there's unequal sharing of electrons, will result in a polar molecule, which means there's a part of that molecule that's going to be more positive, and there's a part of the molecule that's going to be more negative because of the unequal sharing of electrons over the entire molecule. And those that are polar, will have what is referred to as a dipole moment. Not to confuse people, but the dipole moment is represented, strangely enough, by the same arrow. Yeah, so the same arrow is used to represent the bond dipole and a dipole moment overall, what's happening. Nonpolar molecules will not have a dipole moment and means that they are going to share overall the entire molecule. They're going to share those electrons equally, which means essentially it's a neutral molecule. There's not a side that's more positive. There's not a side that's more negative or anything like that. So let's talk about really the easiest ones to do. And as I might have mentioned last time, this is really the only place where bond polarity and molecular polarity are going to be the same. And that is when you're dealing with diatomic molecules. So when you're dealing with diatomic molecules, for example, like H2 that we have listed there, O2, if we were to calculate the difference in electronegativity values for each of these bonds, right, we would get a difference of 0, right? Because they're the same element. So when you subtract the same number, you're going to get 0. That means in each of these cases, the bond is nonpolar, right? Remember, anything from like 0 to 0.4, right, is going to be a nonpolar bond. And because this bond is nonpolar, and each of those molecules that I just drew, how many total bonds are there? There's just one. So if the only bond in the entire molecule is nonpolar, then that would mean that the entire molecule also has to be nonpolar. So in diatomic molecules, if you have a nonpolar bond, then the molecule is going to be a nonpolar molecule. And it's only because there's only one bond, it's nonpolar, so that's the deal, it's over. And that's why it's basically the same as the bond polarity. Now, if you're dealing with things that are different, like HF, HCl, and so forth, we know that the difference in electronegativity here, for example, for this guy, is something like 1.9, which means it is a polar bond, right? Where the fluorine is more polar, right, or more electronegative than the hydrogen. Once again, in each of these cases, because it's diatomic, there's only one bond, which means if that one bond is polar, the entire molecule should be polar as well. And this would mean that these guys are going to be polar molecules. By the way, this arrow would then be called its dipole moment, yeah, heading towards the fluorine, yeah. So it has an overall dipole moment where the fluorine is more negative than the hydrogen in this case. So diatomic molecules are pretty much the simplest ones to figure out polarity because there's only one bond. If that bond is nonpolar, then the molecule is going to be nonpolar. And if that bond is polar, then the molecule will be polar. So like the simplest ones to do. Any questions on that? By the way, as you can see with the oxygen, doesn't matter if it's double bonded, triple bonded. It makes no difference in terms of the molecular polarity. Any questions on that? Once again, that would be nice if everything was that simple, but of course, not going to be. So when we get to 3 or more atoms involved, there's actually 2 things that you have to look at. You have to look at whether or not there are polar bonds. So oddly, if there's not really polar bonds, probably going to be nonpolar. There might be a little exception, but most of the time. Now, if there are polar bonds, you actually have to look at the molecular geometry or the shape of it. So let's take, for example, our friend carbon dioxide that we drew, I think. Now, carbon dioxide, does it have polar bonds? Is the bond between carbon and oxygen polar or nonpolar? We could think about this by just simply looking at the periodic table, right? Carbon and oxygen are in the same period of the periodic table. Yes. Oxygen is further to the right, which means oxygen should be more electronegative and it should create a polar bond. And it is going to create a polar bond. Again, one of those things we talked about earlier, don't really need the numbers to do that sort of comparison. So we will have polar bonds, right, heading this way. And we will have polar bonds heading this way, the bond dipole arrows, right? So we do have polar bonds. So you would expect perhaps that this molecule would be a polar molecule because it does have polar bonds. But we do need to also look at the molecular geometry, which we just did, right? The molecular geometry in this case is 2 electron pairs and 2 bonds, which means the molecular geometry is going to be linear, right? That is basically a straight line. So what we essentially have is, if this is my molecule of CO2, I have oxygen pulling this way, and then I have oxygen pulling the other way. And I'm actually pulling really hard on my pen in both directions. Is my pen going anywhere? My pen is not going anywhere, right? I'm really pulling on it actually, yeah. So because of the geometry here, even though that there are polar bonds, they're actually headed in equal and opposite ways, kind of like tug of war on a rope. Both people pulling equally in opposite directions, nobody's going anywhere. So they cancel each other out, and this guy is actually going to be a nonpolar molecule. So it is possible, and this is a really good example of, it is definitely possible to have polar bonds, but because of the geometry and molecular geometry, they may actually cancel each other out and be nonpolar. The reason for that is these arrows here are what we like to call vectors there in physics, yeah? And vectors have direction, they have magnitude. Then I fell asleep, and then I woke up long enough to remember. In certain cases, they cancel each other out. In other cases, they add to each other. And in cases where they cancel each other out is wherever they're going equal and opposite of each other, like pulling on a rope, are going head on to each other, kind of like pushing a door. Somebody pushes a door on each side that swings open, and they push equally on both sides. The door's not going to open, right? It's just going to kind of stay there. Now, in this case, they do not add to each other. If we take a look at water, which looks something like this, water also has polar bonds, right? With the oxygen being more electronegative, heading in this direction. So water has polar bonds. The geometry of water is the one we did in our example, 4 electron pairs and 2 bonds. That is our bent, our V-shaped. So if you think about sort of water in this case, something like this, we got like a polar bonds going this way and this way. They're going to kind of meet at the top, almost like you pull it on a string from the top. And you kind of imagine the whole thing will sort of move. And they will actually add to each other. And we will get what is referred to as a net dipole moment heading in this direction, where the oxygen side of water is more negative, the hydrogen side of water is more positive, and we will get a dipole moment. And because they will add to each other, that means that water is a polar molecule. All right, I'll throw a little physics that I sort of vaguely remember maybe as I was waking up. You kind of add these arrows like so, and then add them together, get your net dipole heading in that direction. Nobody wants to do that, by the way. I just say no. So in certain cases, these dipole moments or these bond dipoles will add to each other and basically have an overall dipole moment. So as I mentioned before, nobody wants to think about vectors. Nobody wants to draw vectors and figure out which way things are going. So there should be a shortcut, and there is. So let's talk about that shortcut. All right. If you have a molecular geometry of trigonal planar or tetrahedral, and those are the molecular geometry names here. What all these have in common is if you draw the Lewis structures, there are no non-bonding electrons on the central atom. And all the outside atoms are the same. That means that you will get a symmetrical geometry, is what these guys are referred to, being symmetrical. That means all those bond dipoles will cancel each other out because they're equal and opposites of each other, and you will have a nonpolar molecule. So if we drew something like this, and again, I'm not going to draw the dots on the fluorines here. I take a look at this and go, I look at the central atom, no dots, everything on the outside is the same. That's going to be nonpolar molecule. It does have polar bonds, right? Heading towards the fluorines in each of these cases. But because of the symmetrical geometry, they're all going to cancel each other out, and you will get a nonpolar molecule. What happens if I take one of those fluorines and I swap it out for a hydrogen? I now still have these polar bonds, right? The bond between carbon and hydrogen is actually nonpolar, right? Actually heading just a little bit that way. This molecule now becomes polar because you got 3 guys pulling one way, right? And the other guy is not pulling back the other way. So kind of like a tug of war, right? 3 people grab a rope one way, and the other one guy's just kind of like hanging on. He's going to start to move, and it's going to become a polar molecule. So if you have either of those geometries and everybody on the outside is the same, non-polar molecule, any of those geometries, and everybody on the outside is not the same, going to probably be polar. That leads us to unsymmetrical geometries, which in your case is our angular, our trigonal pyramid, and our bent, our V-shaped. What all these guys have in common is there are dots on the central atom, our non-bonding electrons. And if all the elements are the same on the outside, you're going to end up with an unsymmetrical geometry and a polar molecule. So it is almost as simple in most cases as looking at your Lewis structure and going dots or no dots, basically. So for example, if we look at a few here, just to finish up on, take a look here. I drew some a second ago. Yeah, we'll take a look at some of these here. For example, we'll just kind of look at this guy. All right. All right. So I look at this one, right? No dots on the central atom. Everything on the outside is the same. Polar or non-polar that molecule. Non-polar. I look at central atom, no dots. Everything on the outside is the same. Polar or non-polar. Non-polar, yeah. The only one you have to worry about is linear. This one you actually do have to think about, right? So this one's going to be non-polar like we talked about. Linear is the only one that you really will have to think about, but it's a straight line, which means if they're going opposite, they cancel. They're heading towards each other, they cancel. But you could have everybody heading in one direction, which means it would be polar. That one's pretty simple to sort of figure out. This guy would be polar or non-polar. Non-polar. This guy's got dots. Everything on the outside is the same. What is it? Dots, everything on the outside is the same. It's going to be polar. Yeah. How about water? We have dots, right? Everything on the outside is the same. It's going to be polar. We had this guy that we drew earlier. I have dots. Everything on the outside is the same. Going to be polar. Yeah. So that's as quick as you could do molecular geometry. 99.9% accurate. So there's got to be something that might not work. What's that? Yeah. So I would think of it very simple. It's like no dots. All you want to look at is everything the same? Non-polar. No dots, everything not the same. Bless you. Polar. Dots, everything the same on the outside, probably going to be polar in most cases. Again, linear is the only one that you really got to think about, but it is a straight line. So again, if things go opposite in a linear situation, canceling, they're heading right at each other in a linear situation. Those bonds, dipoles, non-polar. But if they're all heading in the same direction, with polar. Question on molecular geometry. All right, that's a nice warm up to the lab of more of this. All right. See everybody in just a bit. You just signed the roll sheet, come sign it. By the way, I think we're going to quiz it up on Wednesday on this chapter 12, bonding and all this stuff.